All right, imagine this. You've got a pile of coins. Seems simple, right? But here's the puzzle. Can you find the smallest amount of money you actually can't make? It's a classic coding problem, and today we're going to crack it with an incredibly elegant trick.
Okay, let's dive right in. The puzzle is exactly what you see here. Given some collection of coins, what's the first positive number, 1 cent, 2 cents, whatever, that you just can't form by adding up the coins you have?
So to make this really concrete, look at this example. If you have coins of 1, 2, and 5, you can start listing out the sums you can make. You can make 1, you can make 2, you can make 3 by adding 1 and 2, but wait, you see that gap? There's just no way to make 4, and that's exactly the number we're hunting for.
So where do you even start with a problem like this? Well, the most intuitive thing to do, the thing that probably pops into your head first, is to just try every single combination of coins. But, as you're about to see, that path leads to a whole lot of trouble.
And here is exactly why that first idea is a trap. If you try to check every possible subset of coins, the numbers get out of control, and fast. I mean, look at this. Just 20 coins means you're checking over 1 million different combinations. This brute force approach, with its O2 to the n complexity, well, it's a total dead end. We need something way smarter.
So that brings us to the real question, right? Instead of just trying to muscle our way through this chaos, can we find some kind of structure? Is there a hidden pattern in here that could give us a shortcut? And the secret weapon is, surprisingly simple. It's sorting. Just by arranging the coins from the smallest to the largest, we can completely reframe the problem. We stop asking, hey, can I make the number 13? And we start asking a much more powerful question. What's the continuous range of numbers I can currently make starting from 1? This, right here, is the heart of the whole greedy algorithm. We're going to use just one variable, let's call it current change, to keep track of the change we can create. And for each coin, we ask a simple question. Is this next coin small enough to help us make the next value in our sequence? If it is, great, we extend our range. But if it's too big, it creates a gap. And that gap, that's our answer. Okay, let's trace this out. We'll start with a current change of 0, meaning we can't make anything yet. We pick up our first coin, which is a 1. Cool. Now we can make change up to 1. We grab the next coin, also a 1. Add that to our range, and now we can make everything up to 2. Next up is a 2 coin, so we add that, extending our range all the way up to 4. Then a 3 comes along, and that pushes it to 7. So at this point, we can make any value 1 through 7.
And we just keep going. The next coin is a 5. Since we can already make everything up to 7, that 5 lets us bridge the gap and now create all sums up to 12. Then we grab the 7 coin. That pushes our continuous range of possibilities all the way up to 19. So far, so good. No gaps in sight.
And here it is, the climax. We've hit a wall. Right now, we can create any amount of change up to 19. That means the very next value we need to be able to make is 20. But our next coin is a 22. It's just too big. We can't use it to make 20. We found our gap. The smallest change we cannot possibly make is 20. I know, it almost feels like a magic trick, doesn't it? So let's pull back the curtain and really break down why this simple, greedy check is absolutely guaranteed to work every single time.
The logic is all about these overlapping intervals. Think about it. If we can already make every number up to, say, x, and our next coin, c, is no bigger than x plus 1, then we're guaranteed to be able to create a new, unbroken range up to x plus c. But if that next coin is bigger than x plus 1, it leaves a gap we can never cross. And sorting is the key that makes sure we always use the smallest possible coin to try and fill that next gap.
And the best part might be just how clean and simple the code is for this. It really comes down to 3 steps. 1, you sort the coins. 2, you loop through them, making that one critical check for a gap. And 3, if there's no gap, you just extend your range. That's it. It's beautifully simple.
So what's the payoff for this elegant approach? Well, it's a super efficient solution. The time complexity is O of n log n, and that's almost entirely because of that initial sort. And get this, the space complexity is O of 1, constant space, because we only need that one little variable to track our change. That is a massive improvement over the first idea.
Now, this isn't just a clever trick for one random problem. This is a powerful mental model you can use, often called the greedy range pattern. This whole sort, track, extend strategy, it's your key to solving a whole bunch of problems involving intervals, or scheduling, or finding any kind of missing value.
Look, in a technical interview, it's not enough to just know the answer. You've got to be able to explain your thinking.
So here's your 4-step game plan. First, identify what kind of problem it is. Second, propose the greedy approach with sorting. Third, justify why it's so efficient. And fourth, verify your logic with a quick example, just like we did. This cheat sheet right here shows you how to turn an algorithm into a really compelling story for your interviewer. Following a structure like this proves you don't just have the answer memorized, it shows you deeply understand why it works. And trust me, that's what they're really looking for.
And really, that's the big takeaway here. The most elegant solution so often doesn't start with some complicated logic. It starts with the simple act of creating order. So I'll leave you with this question to think about. What other chaotic problems are you facing that could be simplified just by taking a moment to sort them first?